Lake Powell has long represented one of the greatest engineering achievements in modern American history. Yet by the summer of 2026, it has become an equally powerful symbol of scarcity. Stretching across the border of Arizona and Utah, the vast reservoir carved into the red sandstone canyons of Glen Canyon once appeared almost limitless. Boats floated above landscapes that had been dry for millions of years. Towering canyon walls reflected deep blue water stretching toward the horizon. For decades, generations grew up believing this enormous reserve would always be there, quietly storing the Colorado River for cities, farms, industries, and nearly 40 million people across the American Southwest. That confidence has steadily eroded. Years of persistent drought, rising temperatures, reduced mountain snowpack, and increasing water demand have transformed the reservoir into one of the clearest indicators of the Colorado River Basin's growing challenges. Vast white mineral stains, commonly called the bathtub ring, now wrap around the canyon walls, revealing just how dramatically the water has retreated. Marinas have been relocated multiple times. Boat ramps have been extended farther into the shrinking reservoir. Islands have emerged where deep water once covered towering rock formations. By late July of 2026, official Bureau of Reclamation measurements showed Lake Powell holding approximately 5.5 million acre-feet of water, representing only about 22 to 23% of its total storage capacity. The water surface stood near 3,523 feet, or approximately 1,074 meters, above sea level. Even though the reservoir still appeared enormous from space, the volume remaining inside it was only a fraction of what earlier generations considered normal. Numbers like 5.5 million acre-feet are difficult for almost anyone to comprehend. Even professionals working in hydrology rarely picture such quantities intuitively. Human brains simply did not evolve to imagine volumes measured in millions of acre-feet or trillions of gallons. Large statistics lose their emotional meaning long before they lose their mathematical accuracy. That is why comparisons matter. One of the fastest-growing industries on Earth offers an unexpected way to visualize the scale of Lake Powell's remaining water. Artificial intelligence has triggered a construction boom unlike anything the technology sector has experienced before. Around the world, companies are racing to build enormous computing campuses capable of training increasingly sophisticated AI models. These facilities contain hundreds of thousands of processors operating around the clock. Every calculation generates heat. Every rack of computers must remain within carefully controlled temperatures to avoid damaging equipment worth hundreds of millions of dollars. Cooling those machines requires energy. In many locations, cooling also requires water. As AI capabilities expand, so do discussions surrounding the environmental footprint of these massive computing complexes. Electricity often dominates the headlines, but water has become an equally important part of the conversation. Some advanced cooling systems consume very little water, while others depend heavily upon evaporative cooling towers that continuously lose water into the atmosphere as heat is removed from the servers. This raises an intriguing question. Exactly how many of the world's largest AI mega data centers would be needed to consume an amount of water equal to everything currently stored inside Lake Powell? The answer is both astonishing and surprisingly easy to calculate. Everything begins with Lake Powell's present storage. An acre-foot represents the amount of water needed to cover 1 acre of land to a depth of 1 foot. That equals approximately 325,851 gallons, or about 1,233 cubic meters. With Lake Powell storing approximately 5.52 million acre-feet during late July of 2026, multiplying those figures produces a volume of roughly 1,800 billion gallons of water. Expressed in metric units, that equals approximately 6 4/5 cubic kilometers. Even these converted figures remain almost impossible to visualize. 1 trillion gallons exceeds ordinary human experience by such an enormous margin that it becomes little more than another statistic. Imagine filling nearly 2 trillion 1-gallon containers. Imagine transporting them across deserts and mountains. Imagine trying to count them one by one. The exercise quickly becomes meaningless because the numbers extend beyond everyday intuition. Instead, consider something far more familiar in today's technological landscape: modern AI mega data centers. Although facilities differ substantially in design, cooling technology, climate, workload, and operating efficiency, many analyses use an upper-end estimate of approximately 5 million gallons, or nearly 19 million liters, of water consumption per day for an exceptionally large AI-focused computing campus employing evaporative cooling. That figure represents a deliberately high-end scenario suitable for illustrating maximum water demand rather than typical operations across the industry. 5 million gallons sounds extraordinary. Viewed another way, that equals nearly 19,000 cubic meters of water every single day. Every sunrise would begin with another 5 million gallons disappearing into cooling systems. Every sunset would close another day having consumed enough water to supply thousands of households for months. The pace never slows. Unlike factories that may pause production, AI computing often operates continuously. Training advanced language models, image generators, scientific simulations, autonomous systems, weather forecasting algorithms, pharmaceutical research, and countless commercial applications requires uninterrupted computing power. Servers remain active every hour of every day throughout the year. Multiplying 5 million gallons by 365 days produces approximately 1,825,000,000 gallons annually for a single mega facility. Now the comparison becomes possible. Lake Powell currently contains roughly 1,800,000,000,000 gallons. Divide that by 1,825,000,000 gallons consumed annually. The result approaches 986 years. In other words, if only one enormous AI mega data center consumed 5 million gallons every day, and if absolutely no new water entered Lake Powell, while no water left through river releases or evaporation, that lone facility would theoretically require nearly 1,000 years to use an amount equal to today's stored volume. One facility clearly cannot threaten a reservoir of this scale, but industrial development rarely stops at one. Technology companies increasingly build clusters rather than isolated campuses. Several neighboring facilities often share electrical infrastructure, fiber optic networks, substations, water pipelines, and transportation corridors. Regions with abundant electricity frequently attract multiple operators simultaneously. Imagine 10 identical mega data centers. Collectively, they would consume approximately 50 million gallons every day. Their combined annual demand would exceed 18 billion gallons. Under the same simplified assumptions, Lake Powell's remaining storage would equal roughly 99 years of continuous consumption. Expand the complex to 50 facilities. Daily demand rises to approximately 250 million gallons. Annual consumption exceeds 91 billion gallons. The reservoir's current storage becomes equivalent to roughly 20 years. Increase the total again to 100 mega data centers. 500 million gallons disappear every day. Annual demand approaches 183 billion gallons. The theoretical timeline falls below 10 years. Even that remains difficult to grasp because Lake Powell still appears visually immense. Boats crossing its surface encounter broad expanses of open water extending beyond the horizon. Towering sandstone cliffs continue reflecting sunlight into narrow side canyons. Yet mathematics steadily compresses centuries into decades as more facilities enter the calculation. Raise the number to 250 mega data centers. Daily demand climbs beyond 1,250,000,000 gallons. Annual consumption exceeds 456 billion gallons. Lake Powell's present storage becomes equivalent to approximately 4 years. Double that again. 500 enormous AI campuses. Daily water demand reaches approximately 2.5 billion gallons. Annual use exceeds 912 billion gallons. The reservoir now represents only about 2 years of supply under this purely hypothetical exercise. Then comes the most remarkable comparison. Multiply the facilities until the annual consumption equals Lake Powell's remaining stored volume. The answer arrives at approximately 986 mega data centers. Rounded for simplicity, roughly 1,000 AI mega data centers, each using 5 million gallons every day, would theoretically consume a volume equal to Lake Powell's current storage in about 1 year. That single comparison transforms an abstract reservoir measurement into something tangible. 1,000 enormous computing campuses operating simultaneously, would collectively require nearly 5 billion gallons of water every day, or almost 19 billion liters. Across one full year, their combined demand would approach 1,800 billion gallons. Those figures align remarkably closely with Lake Powell's present stored volume. It is an extraordinary statistic. Yet it is equally important to understand what this comparison does and does not mean. This calculation deliberately assumes an impossible set of conditions. No mountain snow melts into the Colorado River. No rainfall enters tributaries. No runoff arrives from surrounding watersheds. No water flows downstream through Glen Canyon Dam. No evaporation occurs from the reservoir's broad surface. Every gallon removed serves only one purpose: cooling AI data centers. Real life works nothing like that. Lake Powell exists within one of the most carefully managed river systems in the world. Water enters from upstream reservoirs, seasonal snowmelt, and countless tributaries. Water simultaneously leaves through dam releases supporting downstream states, agriculture, municipalities, tribal communities, hydroelectric generation, environmental requirements, and Mexico under international agreements. The reservoir continuously changes. Its storage rises and falls depending upon weather, policy decisions, runoff forecasts, conservation efforts, and annual demand. Likewise, AI data centers do not all consume 5 million gallons every day. Some use considerably less. Others employ hybrid cooling systems designed to reduce water consumption during cooler months. Certain facilities increasingly rely upon recycled wastewater unsuitable for drinking or agriculture. Some adopt closed-loop liquid cooling that dramatically reduces evaporative losses. Others are being constructed in cooler climates, specifically because lower ambient temperatures reduce cooling requirements. The industry itself continues evolving at extraordinary speed. Direct-to-chip liquid cooling allows heat to be removed more efficiently from powerful processors. Immersion cooling submerges servers inside specially engineered dielectric fluids rather than relying primarily upon air circulation. Advanced heat exchangers improve efficiency while reducing evaporative demand. Waste heat recovery systems redirect thermal energy into nearby buildings or industrial processes instead of simply releasing it into the atmosphere. Every improvement reduces the amount of fresh water required for each unit of computing. Technology companies have also begun reevaluating where future facilities should be built. Regions experiencing chronic drought increasingly face greater scrutiny regarding industrial water consumption. Local governments weigh economic development against long-term water security. Residents ask whether precious freshwater resources should support agriculture, drinking supplies, ecosystems, or expanding digital infrastructure. These discussions have intensified throughout the American Southwest. Communities already adapting to reduced Colorado River allocations naturally examine every significant new water user, regardless of industry. At the same time, computing demand continues climbing. Artificial intelligence requires extraordinary processing power. Training frontier models may involve hundreds of thousands of graphics processors operating simultaneously for weeks or even months. Once trained, those systems continue serving millions of users through inference workloads every hour of every day. Every search, image generation request, translation, scientific calculation, engineering simulation, and automated assistant ultimately depends upon physical hardware somewhere inside a data center. The digital world feels weightless. Its infrastructure certainly is not. Steel buildings, concrete foundations, electrical substations, cooling towers, water pipelines, fiber optic cables stretching across continents, power plants supplying uninterrupted electricity, reservoirs supporting communities where those facilities operate. Behind every seemingly effortless interaction exists an immense industrial ecosystem. Lake Powell reminds observers that even the largest engineered water reserves possess limits. When Glen Canyon Dam was completed during the 20th century, the reservoir gradually filled until it became one of the largest artificial lakes in North America. At full capacity, it stored more than 24 million acre-feet of water, equivalent to nearly 30 cubic kilometers. The reservoir became a strategic savings account for the Colorado River Basin, capturing wet years to help survive dry years. The challenge confronting managers today is that dry years have become increasingly common. Scientists continue examining the combined influence of prolonged drought, higher evaporation rates associated with warming temperatures, altered precipitation patterns, declining snowpack, and growing demand throughout the basin. While individual years sometimes deliver encouraging runoff, the long-term trend has placed sustained pressure upon both Lake Powell and Lake Mead. Every additional gallon conserved therefore carries greater importance than it once did. That conservation extends beyond households shortening showers or replacing lawns. Agriculture continues exploring more efficient irrigation. Cities invest in recycling wastewater. Industries redesign manufacturing processes. Power plants adopt alternative cooling strategies. Technology companies examine methods to reduce both electricity consumption and water demand. Innovation increasingly revolves around efficiency rather than unlimited resource availability. The hypothetical comparison involving 1,000 AI megadata centers serves precisely because it converts an incomprehensible reservoir into a relatable scale. People understand that 1,000 gigantic computing campuses would represent an astonishing concentration of digital infrastructure. Visualizing them spread across deserts and industrial parks immediately communicates the immensity of Lake Powell's remaining storage, while simultaneously highlighting the growing resource demands accompanying the AI revolution. It is neither a prediction nor an accusation. Instead, it demonstrates proportionality. Even at today's reduced level, Lake Powell still contains an immense quantity of water. Yet modern civilization is constructing technologies whose cumulative resource requirements continue expanding at unprecedented rates. Future progress will likely depend upon ensuring those technologies become dramatically more efficient rather than simply dramatically larger. Perhaps the most fascinating lesson emerging from this comparison is not the reservoir itself, but the extraordinary pace at which humanity is reshaping its relationship with natural resources. During the previous century, discussions about water largely centered upon farms, cities, factories, and hydroelectric dams. Today, conversations increasingly include supercomputers training artificial intelligence. Digital progress now intersects directly with hydrology. Cloud computing intersects with reservoir management. Machine learning intersects with climate adaptation. Infrastructure once considered entirely separate has become interconnected. Water supports electricity. Electricity supports computing. Computing accelerates scientific research that may improve water forecasting, optimize irrigation, predict drought, design better cooling technologies, and even assist engineers developing more sustainable infrastructure. The relationship works in both directions. Artificial intelligence consumes resources, yet it may also help society manage those same resources more effectively. Standing along the shoreline of Lake Powell today, visitors still encounter breathtaking scenery unlike anywhere else on Earth. Massive sandstone cliffs tower hundreds of feet above emerald coves. Narrow slot canyons disappear into labyrinths carved by ancient rivers. The reservoir remains magnificent despite its reduced elevation. Hidden beneath that beauty lies one of the most remarkable mathematical comparisons of the modern technological age. Based upon Lake Powell's current storage during late July of 2026, approximately 1,000 AI mega data centers, each consuming about 5 million gallons, or nearly 19 million liters of water every day, would theoretically use a volume equal to the reservoir's entire remaining storage in roughly 1 year. Assuming no inflow, no rainfall, no snowmelt, no downstream releases, and no other competing uses. It is an astonishing statistic not because it predicts the future, but because it reveals the immense scale of both the reservoir and the rapidly expanding digital infrastructure defining the 21st century. One represents the accumulated waters of an iconic river system. The other represents humanity's accelerating pursuit of artificial intelligence. Together, they illustrate a reality becoming impossible to ignore. Every breakthrough ultimately depends upon the finite resources of the physical world, and the choices made today will determine whether those resources remain sufficient for generations still to come.